Hello everyone. In this video we will continue to examine topic 7.2 nuclear reactions and the relationship between mass and energy. In the last video I ran through sort of the introduction to the special theory of relativity, and we introduced the first two postulates. In this video we are going to consider what the results are, okay? And I'm just going to give the briefest of treatments. Truly this topic is worthy of more time and attention, and if we do the option, we will give it that, or perhaps you might see it in your undergraduate physics education. The first thing that can be proven as a result of these two postulates, that is, if you take those two postulates, that the laws of physics are the same in all inertial reference frames, and that the speed of light is constant and equal to c in a vacuum in all inertial reference frames, you derive an effect called length contraction. And fundamentally, what's going to happen is that if you take these postulates and apply them to situations where light is kind of doing what we described in Galileo, you find that the only way to justify it is the only way that this can be true is if length and time do not work the way we thought they did. That is, if distance and displacement and time do different things. The first effect is known as length contraction. And as it turns out, objects in motion, okay, so if you're watching an object move, like a cart that's moving, here it is still, here it is moving fast, shrink along the axis of motion relative to a frame of reference. So you're standing on the ground and you watch the car move, it literally is smaller measured from your frame of reference. Now, if someone were on that moving car, they themselves would not measure it to be smaller. They're in their inertial reference frame, and they will measure the cart to still be the length L. In fact, what they will measure is that because they see you moving, like someone in a car, seeing the world moving outside them, they will see everything else shrink. And that is not an appearance, although I use the verb see. They literally get smaller. And moreover, there is no fact of the matter about how long, how extended things actually are. It depends on how fast they're moving in your reference frame. There's no truth about what length it is. Now, you can talk reasonably about the length of the car when it is not moving, or in its own reference frame is how we'll describe that. That's the longest that car will ever be measured to be. But anything else that views the car as moving, okay, views the car as moving. Notice I say that rather than anything else that is moving, or no, doesn't matter. As long as that other thing is viewing the car as moving, then it will measure it to be a shorter length. Okay? That's known as length contraction. And that already seems pretty weird, but actually that's the easiest of the relativistic effects to digest. One thing to note is that this effect, this relativistic effect, only becomes really, really significant at significant fractions of the speed of light. So 10%, 20%, 30%. And in order to really see the effects, you need to go to 90%, 95, 98, 99, 99.9, etc., and so on. So this only works, or these effects are only noticeable really, really close to the speed of light. This is why we don't notice them in everyday occurrences. I will say, though, that we need them. If you do not account for the special theory of relativity, your GPS will give you a significantly wrong result for where objects are. So length contraction is a real and measurable effect that happens as a result of these two postulates. One more thing that happens is time dilation. And in many ways, I think this is much harder to digest than length contraction, much harder to accept. And time dilation is the following effect. Time ticks slower for objects that are moving. Okay? Not clocks tick slower, but everything experiences less time from your perspective for objects in motion. So if you put a clock, for example, on that moving cart, and that clock is moving fast, it will literally tick seconds off at a slower rate compared to a clock that is in your frame of reference on the ground and not moving. Time ticks slower for objects in motion, and it's the same rules that apply for length contraction. So if that clock is on the object, on the cart, and from the clock's perspective, it views the rest of the world as moving, then it will see the rest of the world as ticking slowly, whereas it ticks normal. So the shortest times, the shortest times that anything takes, the shortest time interval that anything takes will always be measured in its own reference frame. This seems weird to us and is responsible for a number of apparent paradoxes, including the twin paradox, which I will explain at a later point. So perhaps you might accept length contraction and time dilation, but length contraction and time dilation lead to the following idea, which seems really, really, really hard to accept, and that is known as the relativity of simultaneity. If time dilates, then if any two events are separated in space and time by a smaller distance than it would take for light to travel between them, there is no fact of the matter about the relative timing, which happened first. Okay? So here's the idea. Let's say you and I both clap, and we clap at exactly the same time. Boom. All right? But now, relative to both of us, someone is moving, and moving sort of off axis at a diagonal, and they're moving very fast. Well, from their perspective, we're moving very fast, but if we're off axis, one of us will appear to be moving faster than the other. And so with the ideas of length contraction and time dilation, you can actually account for this, and as it turns out, one of us will end up clapping first. Okay? One of us will end up clapping first. That means in our reference frame, two things happen simultaneously. But in their reference frame, one of them happened first. Moreover, any reference frame you want can be chosen at any time, which means it's not true that things happen at the same time. That's not a sentence that, as it turns out, makes sense. It's only true that things happen at a certain time in a specified reference frame. Okay? This has some wildly counterintuitive consequences, and is in some ways the hardest fact of this to accept, that this idea that there is no true sort of big time along which you can keep track of everything. And not only that, but things that might appear to happen at the same time in one frame of reference, one of them will precede or follow the other in another frame of reference.